Hi, in a previous video, which I'll link in down below if you haven't seen it, we played around with a precision 1 amp current source. Ignoring all this sort of stuff, we were basically following the application note circuit here in the LTC 6655 datasheet. This is a precision 1.25 volt voltage reference, and this thing oscillated to buggery. It was absolutely awful, and since then I've tried a couple of I've tried the other recommended configuration with the PNP because I suspected this thing might oscillate. That's why I breadboarded the thing up. Never trust these application notes just to work. Oh, you got to build the things up and test them, let me tell you. And since then I've tried various configurations. I've tried the other one here with the PNP configuration, but that one was a dog too, especially at higher currents. And I tried some FETs and other configuration and various other things to try and stabilize the loop on this thing, because internally it's an op amp, and well, you know, if you don't get the loop stable, which I won't go into, it can oscillate, and that's exactly what we saw, especially at high current load. So I thought I'd have another crack here using another circuit you've seen before, which I'll link in down below as well if you haven't seen it. This is just my simple constant current dummy load, but well, hey, a dummy load, it's constant current, right? That's exactly what we need. 1 amp. I don't necessarily need the ground referenced output that we had on this circuit here. You can see the transistors in the upper half, and the output current actually goes down to ground like that. Well, don't actually need that because it's going to be battery isolated anyway. So I figure my load can be on the high side. So I thought I'd go back to this configuration I've used before, which can also be unstable, of course. You know, nothing new there. It's still got a loop in here. It's still got the op amp and everything else, and you have to stabilize that loop. But I thought I'd give this one a crack and see what we get. So we're going to build it up on the breadboard here. I've got my N-channel MOSFET. I just pulled one out of the junk bin. It's an RFP 3055, and I've now got, which is very nice, from Vishay. Thank you very much, Vishay, for sending me samples of these very nice 1.25 ohm 4-terminal 0.02%, I think it is, precision resistor. Really quite nice. So this will actually allow us to get a very nice 4-terminal wire measurement even on a dodgy breadboard, which we're going to see. And I'm using the same thing. Oh, I didn't write it in there, but yes, it's still the LTC 6655. I'm going to still stick with that. So 1.25 volts over 1.25 ohms is going to give us a constant current of 1 amp. But hey, let's build it up, see if it oscillates. It probably will. Well, we can almost certainly make it oscillate under certain circumstances. The output capacitance here, and the load current, and the input capacitance, and all sorts of stuff. So yeah, we probably can get it to oscillate. But let's see if we can actually get a precision 1 amp current source on our breadboard, which we intended to last time, because these configurations up here just sucked. As I said, thank you very much, Vishay, for sending me samples of this 1.25 ohm. There's the exact part number there. If you're playing along at home, you can actually order these on DigiKey, but I think there's a minimum volume to actually order them. So it's a 1.25 ohm, 0.02%, and it's the VPR 221 series. I'll actually link in the datasheet down below. Really awesome Tempco, fantastic resistor for using in a precision current source like this. And here's the little strip they come in. They sent me a few of them. And well, if you're going to make them, because these are made to order, actually, you can order any value you like, and they will laser trim it for you. Vishay are fantastic. And yeah, there it is, a 4-terminal TO220 package. Fantastic. So the two outer pins on there are the current in and out, and the two inner pins are the two sense pins in here on our circuit. So even on a dodgy breadboard, we can hook this thing up and get really precise 4-terminal measurements, because the two sense pins are tapped right inside right on the resistor in there. Hence why I'm going to use a really nice precision resistor like this. So we've got our like 0.02% precision voltage reference here. We've got our 0.02% precision 4-terminal resistor, worst case, of course. So we should really be able to get, you know, like a 0.02% or better 1 amp current source reference out of this sucker. But even if we do get this thing stable and build it up, there's going to be an issue with this circuit, and I've deliberately left it out. And if you want to try and figure out what it is before we get to it in the video, hopefully I can get the thing stable and we can actually see there's going to be some output error here. We're not going to get precisely 1 amp, and try and figure out why. So you can stop the video now, look at the data sheet for the LTC 6655, try and figure out why we're not going to get precisely 1 amp through this resistor. So this is the circuit we're going to build up on the breadboard here. As the datasheet recommends, of course, the sense line must have a bypass cap of at least 2.7 microfarads and less than 0.1 ohm ESR. It's got to be a low ESR because the transfer, function, if you look at the loop stability and all that sort of stuff, you can't have too high a value ESR. The ESR is an equivalent resistor in there like that. So I've got a 10 microfarad ceramic in there, should be good enough. I've got a series resistor in here. I think I've got a 12k, I think it is, just because the gate capacitance, we just want to slow this thing down. We just want to add some roll off in there. So you want to put a series resistor in there of some nominal value. So it can change, and maybe we might experiment with that. But anyway, I've just got like a 10 or 12k in there, no problem. Just a bypass cap on the input here. They recommend 100N or something like that. I've got one directly from the last video. I got one directly 100N directly soldered onto the little surface mount module, plus for good measure I've got another, I think, 47N outside of that on the breadboards. Oh, by the way, input supply here, we're probably going to need like 4 or 5 volts or something like that. Our output voltage is 1.25 volts, but we've got to have our gate, a sufficient gate drive voltage as well for our N-channel FET over here. I haven't looked at the data sheet for this 3055, I don't actually remember, but yeah, 4 or 5 volts should be good enough, so I'll set it to 5. Oh, also an important thing is that the ground reference for this entire circuit, I'm taking off the sense tap for that resistor there, so there is no error, because we're trying to generate a very precise 1.25 volts across this point. And so basically the sense output, the force line drives the voltage for that, but the sense line here and there, that's our internal voltage reference, is going to produce, or going to try and produce, 1.25 volts precisely across those 2 points. So you want them directly across your sense line there. You don't want to make the mistake of connecting this ground through to here like this. You want this actually returning. If your input is like this and there's a ground there, you want actually your return current bypassing all of your precision voltage reference circuit in here and going back to your supply like that. So you've got 2 current loops there. One is the huge 1 amp current loop going around like that, and the other is just a separate ground in there for this sense resistor. And this chip's only going to draw a couple of milliamps, but you definitely want that. Very important. That's why we're using a 4-terminal resistor. If you don't have a 4-terminal resistor, then you want to do a proper Kelvin connection right on the point. And there is our circuit build up there, and this op amp isn't used here. That was just from some experiments from last time. We may need that again, we'll see. There's our precision voltage reference on there. As I said, bypass cap on the input. The ground, you'll notice that the ground is separate and actually goes back to the sense terminal over there. There's my 1.25 ohm 4-terminal precision resistor. There's our N-channel MOSFET up here. This will be my current source going from the drain of that thing up to the top there. There's my 10 microfarad output cap there. So let's hook this thing up and plug that in, and I'll just measure the output sense line with the scope here, and we'll see what we get. And here's our power supply. I've got it set to 5 volts here, but of course you want to set the output current limit just so you protect your circuit. You don't want to blow the arse out of the thing. So I'll set that to 1.1 amps there, so it can't go over that. It'll self-limit. By the way, no, I don't have any heat sinks on these devices here. The 4-terminal precision resistor is only going to dissipate 1.25 watts maximum, and that is within the safe operating range of this thing, just into free air like that, what's called free air, so without a heatsink, so that'll be fine. The MOSFET over here, no, it's going to get pretty hot. Use Ohm's law, work out how much power is dissipated in that, but hey, it'll be good enough for just, you know, probing for, you know, 5 seconds and seeing if the thing oscillates. It's, you know, it's not like we're going to leave it there for, you know, an hour or something like that. It'll just cook the thing to death. So here we go. Let's see what we get. Let's switch this on, and my circuit's drawing 4 milliamps there. That's sort of what you'd expect for the quiescent current of the circuit here. And if I plug in my scopes hooked up, I'm at 200 millivolts per division. That'll do. Let's plug in our load. Hello, hello. We're getting our 1.25 volts nominal up there, but yeah, it looks like we're getting some oscillation. And if we AC couple that, it looks like, yeah, that's pretty horrid. We're getting about 50 millivolts peak to peak oscillation on this thing. That's pretty awful. Let's see if we can trigger off that and see what we're getting. Ugh, yeah, blah. Look at that, awful. Similar to what we were getting last time. So hey, but you know, we're getting there, and I reckon we can stabilize this sucker. We should be able to. So what I'm going to do now is actually hook up my ammeter here, and let's see what value we get, because you know we should get. There we go. We're getting near our amp, but of course, oh, here we go. It's changed. Look at that. Our waveform there has changed because we've got some extra inductance in this lead. We only had a little jumper lead before, so there you go. That's kind of expected, that you wouldn't get precisely the same waveform. And to show you that, let's put that back in, and I'll show you that that's. There we go. Yeah, completely different. There you go when you add the short, because you got the inductance of these leads in here. So that is changing the whole oscillation frequency of that thing due to, you know, the inductance of this, the ESR of the output caps, and the loop stability in the poles, and the whole, you know, the whole shebang in there. And just to show you that, that's what we're getting, okay, with the huge leads on here. Let's remove the input capacitance. You know how I said I've got the 2 input caps there? Well, let's physically take out one of them. I've still got one there directly on the input of the chip, but we should expect a little change, and we do get it. Look at that. We're getting some more high frequency parasitics happening there. That's really, yeah, that's, look at that. So if we whack our cap back in, and bingo, we're back from the future. But if you think you're going to solve this problem by, you know, tweaking your input capacitance on over here, then you're completely wrong. You're in the wrong ballpark, because the loop stability of this thing is ultimately determined by the phase margin of the output op amp in there for this voltage reference, and the, as I said, the output capacitor here, the 10 microfarads with the it usually specifies in the data sheet, it does in this case, of it's got to be less than 0.1 ohms, but it's not just the ESR of the output, it's actually the output capacitance as well. So this is where we need to solve our problem, and when you get oscillation on a voltage reference or a regulator like this, usually you're not going to have enough capacitance on the output to ensure loop stability in your voltage reference here. Let's increase the value of that output cap, and I think we're probably, well, hopefully we will solve our issue. That's the plan anyway. So let's whack on a big ass, not a huge value resistor, but a big ass 22 microfarad 400 volt electro on here, and see if that makes a difference. So I'm not going up in value yet, but I'm adding another, I'm still leaving in the 10 microfarad ceramic cap which we got in there, but adding another 22 mic in there in parallel. So let's, yeah, that's on. All right, let's switch this back on. No, that hasn't solved it, but it's changed it. Look at that. We're on our way. So let's go up in capacitance, shall we? 470 microfarad electro, 10 volts. So let's give that a whirl. And there we go. And I'll plug this in live here. Let's see what we get. Oh, hello. Hello. Oh, 1.0027. Look at that. We're AC coupled here on the noise, by the way. So that's 5 millivolts per division. Beautiful. We're getting our precision current source near enough to 1 amp. Ah, beauty. What a Bobby Dazzler. So we're down at 5 millivolts per division here, and if you're curious about that noise, I've got the thing actually switched off now. All right, our circuit is switched off and we're still picking up this crap. Okay, so, ooh, hello, look, just putting my hand there is enough to pick up the interference from the screen here and near my circuit and couple that in. There's all sorts of AC coupling stuff happening here. So that is not actually the residual noise of this circuit, and we won't go into actually measuring the noise of this thing. That's why if I switch it on, and because this is actually a pretty low noise reference, right? So the noise isn't actually oscillation of the thing. Here we go. Let's switch it back on and get our, there we go. Noise is exactly the same because we're not using proper low noise measurement techniques here. This noise is a furphy. It's a red herring. So, you know, don't think that is your output oscillating or being noise or anything like that. No, that's not necessarily so. But anyway, all we're here for today is to stop the oscillation, and we have ourselves a stable precision 1 amp current source. Or do we? Now, as I said before, I gave you a little quiz at the start. This is actually expected. The exact value we're getting here, please don't let me scream at me if I'm leaving this on too long, because that FET's going to heat up. Anyway, if I talk too long, which I always do, the output is pretty close to 1 amp there. Look at that. And you might think that's bang on, but do the math there. That's 0.27%. And you remember, this thing should be 0.02. It should be an order of magnitude better than that. So that should be 1.00027 or something like that. And it's not to do with the layout of my circuit, because I'm pretty confident that is right, because we've used the proper 4-terminal Kelvin resistance. So we've got an extra 2.7 milliamps in there. Why? Now this, of course, is where you have to read the data sheet. And if you're reading it carefully, or if you've seen the forum before where we've actually discussed this after the previous video, then you'll notice that pin 6 Vout S, right, that sense line coming back in, you might think, well, it's not going to take any current at all, right? It's going to be the input to the op amp, but it's not. And look, we've got 2 internal resistors in here. There is going to be some current flowing into this pin. And if you read up here, what does it tell you? This pin sinks 2 milliamps. The output error is the resistance of the PCB tray, so that could matter, and it talks about this in the data sheet. I recommend you read it, times that 2 milliamps, regardless of the load current. Aha! 2 milliamps. Bingo! Oh, shit, I left this on. Oops, should be smoking now. It's dissipating 4 or 5 watts in that poor little sucker. That's where our 2 milliamp error's coming from. Gotcha. Oh, poor little sucker. So what we've got happening here is, here's our load up here, here's our ammeter. We've got yes, we do have a precise 1.25 volts across our precision 1.25 ohm resistor. Yes, so we are getting precisely 1 amp flowing through here like this, down through the resistor and out the bottom, but we've got a 2 milliamp error current coming down here and going, oh, thank you, I need to go in there, down to ground. So we've got a precision, even though we've got that precise voltage across there, our resistor, we think, oh yeah, we definitely have to generate our 1 amp through there. That's Ohm's law. Aha, you forgot about this sneaky little current path going down there, little bastard. And that's where our 2 milliamp error is coming from. In this case, it's only 0.2%. So it's not much, but hey, we're trying to design a precision current source here, a 0.02%. Order of magnitude better, 10 times better than that. So that 2 milliamps is killing us. So what we need to do is actually put an op amp buffer in here like this, positive, negative, so then of course there's no current flowing into that op amp because it's a high impedance input, so the error is going to be negligible, not even half a bee's dick, and all of the current, of course this is powered from plus V up here, so all the current is coming from this terminal up here, that extra 2 milliamps is sourced from up here instead of through our load over here. So therefore, if we add in that buffer, which may affect the loop stability of this thing, of course, so hey, we could be back to square one with our loop stability. We may have to compensate, but anyway, that is the way that we're going to fix that. But of course, if you're astute, you would have realized that, look, we've still got our 10 microfarad, in fact, our 470, sorry. What did we use? Like a 470 microfarad in there to make it stable on the output of this op amp now. And hey, op amps do not like having large capacitance on the output. So that thing could oscillate on its own. So we're going to move that cap back over to the input here, and so I'll put that 470 mic back on the input there, and there'll be nothing on the output of this op amp. It'll just be driving that sense line directly. Let's see what we get. Alright, let's switch this sucker on and hook it in. I got my 470 mic on there. I hope it's alright. I've got my op amp in there, it's powered, and fingers crossed. Hello? Ha! Look, no noise. And look, we're down to 0.1.0006, so we're now 0.06% accurate. Awesome. So you remember we were getting 1.0027 before, and the data sheet said, well, it was a nominal 2 milliamps into that pin. Well, we've eliminated that 2 milliamps. It's vanished, and now we're just getting that 0.7. We're getting like 0.7 before, well, 0.0007 before in terms of offset if we didn't account for the 2 milliamps. Take out the 2 milliamps, there we go. Bang! I'm curious to know what happens if we remove our 470 mic cap now. Let's see if it goes back to being... No! There we go! It's still stable. We've got a bit more noise, but not a problem at all. So this thing is now stable without that output capacitance there, because we've entirely changed the loop parameters of this circuit, the poles and everything else. The whole thing has completely changed by adding the op amp buffer in that feedback loop. Oh, hello. I just put in a 10 microfarad ceramic. I was just going to boast that putting in this op amp has ironically made this thing more stable, but look at that. That's horrible. That's 10 millivolts per division there. So that's that little 10 microfarad ceramic. It doesn't like that at all. But if I put in that, well, it works without it, or with the 470, but looks like that 10 microfarads is in the sweet spot, which makes a little bit of oscillation within the loop we've got here. So that's why this kind of circuit you can make stable for one precise load you've got, and that's what I'm going to use this for, is a precision 1 amp current jetter, and that's fine. But if you're using this to power all sorts of different loads at different currents, then, well, you could come a gutser. So just be careful that getting loop stability in all sorts of circuits like this is not easy. And really, unless you've got the exact simulation model of that reference chip, I better turn that off, it's getting a bit hot, then you really have to build this thing up and, try it on your actual load to make sure it works. And that's what we get if we put in 100 nanofarads. Look at that. 100 nanofarads, by the way, I'm putting these caps directly across the sense line of the input of the op amp there. So there you go. That's 50 millivolts per division. That's that 100N. Pretty horrible. So it looks like we still do need that high value cap across here to make this thing stable. Not surprising. And you know how I said this gate series resistance in here is going to matter at the moment? I've got a 12K resistor in there just to slow the thing down, because we're going to get some gate capacitance here and we can cause the thing to oscillate that way. So what I've got now, okay, let's actually short that out. There's our output. Okay, it's stable. I've actually got no capacitance here at the moment, but you can see with the 12K resistor in there, it's nice and stable. Now what I'll do is I'll short out that, there we go, I shorted out that 12K resistor Haha, look at that. So we've got some pretty darn awful 500 millivolts per division noise there. So let's, with that shorted out resistor, let's see if we can, on even our 470 mic cap across our sense resistor there can't, can't settle that oscillation down. We really have to remove that. We really have to include that 10K in there. So the other thing to note about this is that this thing really doesn't change much, even though these devices are heating up. I mean, they're, way too hot to touch. The FET's probably up at 100 degrees, 80 or 100 degrees or something now, and, the 4-terminal precision shunt resistor, might be at 60 degrees or something. I don't know. I haven't put a thermometer on there, but yeah, getting pretty warm. So, but look, I mean, it's pretty ultra stable. That's because this, if you go have a look at the data sheet for this precision resistor, its Tempco is bugger all. These things practically have no drift at all, like 2 ppm per degree C. Oh, and if you're wondering what op amp I used in there, yes, it does actually matter. I've used a really precision trimmed op amp, the OPA the 376 VOS offset voltage of 5 microvolts typical, which translates to with our 1.25 volts here of 0.0004% error. So it's adding bugger all error into our circuit here, and that's what you want. And I just tried another 4-terminal resistor in here because we are still getting 0.006%, which is higher than we'd like, so higher than what we really expect. So I tried a different one, and there you go, it hasn't changed by a huge amount, as you'd expect, because these are 0.02% precision resistors, or better, and I'm sure they're actually better. That's sort of worst case. These things never hit their worst case. So I can only presume that extra error that we're getting in there, because we expect better than that, is due to the contact resistance on my breadboard in here. So this is not ideal. Either that or my voltage reference is out of tolerance. So what I've done is I've soldered up another chip. This is the old one with the dodgy pins that I had to bend inwards to make it fit. Anyway, I've soldered on a brand new LTC 6655, and let's have a look at what we get. Bingo! That is half, I think, roughly half of what we were getting before. So we're now 0.03%, and technically that's within inside our error budget, because our because the voltage reference is 0.025%, I believe, nominal in itself, and then we've got the precision current shunt of 0.02%. So yeah, there you go, within our error budget. So maybe, I don't know, maybe this little puppy has had a bit too much abuse from all the experimenting that we've got there, but I'm pretty happy with that. It's more than good enough for my application here. So there you have it. There's our precision 1 amp current source, and we got it stable, and we got it to work on a breadboard. Brilliant. That's what we want, even within our error budget of our 2 main parts here, which is our voltage reference and our precision resistor here. So I think I might do a custom little board for this. I'm not sure exactly the final form factor it's going to be built in. Little box. It's going to be powered from batteries. It's going to be powered from like 4 D-cell batteries. I didn't test the input voltage range there. The voltage range can perhaps go down a bit. I'm not sure. I'll probably add like a little low battery indicator or something like that. But this is going to work a treat. And of course that FET there needs a heatsink. Technically this resistor here, precision resistor, doesn't need a heatsink, but I would put a small heatsink on that as a matter of course. And this one, yeah, got to test it over, over continuous load and all that sort of jazz. But geez, pretty darn happy. And if you're curious to know what the switch on performance of this current source is, with the 470 microfarad cap across there, so let's give it a go. Little dodgy alligator clip here. So, yeah, there's our contact bounce. There we go. That's pretty dodgy. Let me try that again. So, yeah, there's a switch off, and let's see if I can get a clean switch on. There we go. That's pretty clean. That little bit of noise in there is just from my contact bounce there, but that turns on pretty nicely, but you're only going to get that nice turn on with a large value cap in there. If you've got, you know, a smaller value or no value at all, as we found it was still stable with no value cap in there, then, well, your transient performance isn't going to be smooth like that. It's probably going to overshoot. In fact, you can probably give that a go. Here we go. So I've taken the cap out, and whoa, there we go. Now let me try that again. It's hard to capture. I need a proper switch. There we go, got it. There we go. Got a massive amount of overshoot there. So our 470 mic helps with that. So it's a fairly clean switch on with that 470 mic value. So there you go. I hope you enjoyed that video of this Precision 1 amp current source, and yeah, it's good enough for my application. We were getting, you know, 0.03% here on the breadboard. Not a problem. Its switch on performance seems quite stable, so I'm pretty happy with that. More than good enough for my application. So I'm going to build this sucker up and use it. And if you want to have a play around with it, by all means do yourself. So thank you very much, EEVblog at Vishay, for getting me that Precision 1.25 ohm current shunt resistor. Awesome. I'm going to link in the data sheet for that thing down below. Highly recommend you take a look. Vishay make some awesome resistors, and they actually sent me some other goodness as well, which we might take a look at one day. Very, very nice. Top of the range precision resistors. Resistor porn. Love it. Catch you next time.